So the unit circle is a special circle that has a radius of 1, and we work with it in degree measure and radian measure. So it looks a little chaotic, these pictures perhaps that are here, but it's recognizing that we start at 0 degrees or 0 radians, and the same way we work with our quadrants, we work our way counterclockwise around the circle. So starting in quadrant 1, and then we travel to quadrant 2, and then 3, and then 4. Working again with negative angles, we would just be going in the opposite direction instead. So in that one, we would just travel through quadrant 4 first, and then 3, 2, 1. The degree measures, again, all build, and then the radians are just reduced for their fractions, but it's easy to see where they come from. We'll take a look. To complete the unit circle, it deals with the coordinates that we identify, and they come from special right triangles. And so this is a little table that we had out of the book that gives us some of these ratios that right now might just seem like magic, but my two special right triangles, I either have a 45, 45, 90. So in my 45, 45, 90, my two legs are the same. The hypotenuse actually is the radius of the unit circle. So that's always equal to 1. And then it's a matter of how do we find those two sides. So since they're the same, we can just call each of them a. And so a squared plus a squared equals 1 squared. So we would have a 2a squared equal to 1 squared, or just 1. So if I divide both sides by 2, then I have that a squared is equal to 1/2. So whenever we take the square root of both sides to solve for a, we end up with the square root of 1/2. That can be rewritten as the square root of 1 over the square root of 2, which really is just 1 over the square root of 2. And then there's something we don't have a whole lot of practice with, but it's called rationalizing the denominator. And it's because we don't want radicals to be in the denominator. And so you multiply by whatever that radical is to get rid of it. So 1 times the square root of 2 straight across the top leaves me with just the square root of 2. And then the square root of 2 times itself, you can either think of that radical squared and they undo each other, or you can think of it as the square root of 4, which simplifies to just 2. So that middle column, the sine of that degree is the square root of 2 over 2. The cosine is that value. When we look at our unit circle, the sine is just simply the y coordinate, and the cosine is the x coordinate there, and then tangent is the ratio of sine over cosine. So first row divided by second row gives me the third row of that table over there on the left-hand side. You do not have to explain where these values come from again. Recognizing that they come from special right triangles is important, but that's really all that you need to worry about. The 30, 60, 90, whenever we worked with this one in geometry, if that was my 60 and this was my 30, an easier way to work through this, if you remembered, the hypotenuse always was twice the shortest side. So if I called my short side B and my hypotenuse 2B, and then going back to remembering that in the unit circle, that's always equal to 1. My remaining side was the shorter side times the square root of 3. So in this case, if I solve 2b equals 1, I see that b is 1/2. And so you can see that 1/2 coordinate here in the first row, first column, and here in the second row, third column. And then b square roots of 3. So if I take b square roots of 3 and b is 1/2, 1/2 times the square root of 3 can just be rewritten as the square root of 3 divided by 2 instead of multiplied by 1/2. So we can see where some of those other values come from as well. So now piecing all of these parts together. So all of those special angles from up above, and then these special coordinates that we have here. And it really works to works best, I think, to follow a pattern with these values. So where all the degree measures came from, and we'll work with degrees first. And I typically put them on my radii, if we think of this as the origin here at the center. So if I start with 0 degrees, if you can ignore the middle line for a second, you can potentially see that this has been split into thirds. And if I know that I have 90 degrees here, then split 93 ways tells me that I'm counting off by 30 degrees. So if I count 0, 30, 60, 90, another 30 would be 120, skip the middle, and then I would have 150, 180 degrees. We should recognize doing a 180 is just turning around. 210 degrees, ignore the middle, 240 degrees, 270, 300, ignore my middle, 330, and then I could get back to 360 degrees if I wanted to recognize that I had come full circle. So in degrees, if you count off by 30s, you get all except for those 4 middles that we ignored, which really are the middle. So if I cut 90 in half instead, this is 45 degrees. So you could think of it by counting off in 45s, or recognizing that it's halfway between 30 and 60, which is half of 30. So it's 15 degrees apart. So that leaves me with a 135 over here and a 225 down in the third quadrant, and then a 315 here in my fourth quadrant. Those are my degrees. That was super fast. Rewind, take another look at it, try to do it on your own, see if you can make sense of where those values come from for degrees. Next, we have radians, and radians are similar to my degrees. If I remember my conversion between degrees and radians. So 0 degrees is the same thing as 0 radians. So I'm writing my radians in blue. A 180 degrees was equivalent to pi. So that means that 90 degrees is pi over 2. Pi, another pi over 2 takes me to 3 pi over 2. So up above, these were all already simplified. But if we think of, again, ignoring the middles, if I had 30 degrees that I counted off by at the top, 30 goes into 180 6 times. And so if 180 is equivalent to pi, then I'd really be counting off by pi over 6s. And so this would be 1 pi over 6. This would be 2 pi over 6. This is the same thing as 3 pi over 6. 4 pi over 6. 5 pi over 6. And pi is like 6 pi over 6. 7 pi over 6. 8 pi divided by 6, 9 pi over 6, 10 pi over 6, and 11 pi over 6. And then again, all of these simplify. So instead of pi, 2 pi over 6, sorry, up here, 2 over 6 is really 1/3. So that's like pi over 3. So again, recognizing that 30 fits into 180 6 times, 60 fits into 180 3 times. So I could have looked at my pi over 3, and over here where I had 4 pi over 6, that's really 2 pi over 3. 4 over 6 is the same thing as 2/3. And then again, my 6 pi over 6 really just simplifies to pi, the 7 pi over 6. But if I was again counting by 3s, then pi would be 3 pi over 3. 8 pi over 6, those are both divisible by 2, so that becomes my 4 pi over 3. 5 pi over 3 jumps over here to where I had my 10 pi over 6, and then the 11 pi over 6 didn't simplify, and neither did my 7 pi over 6. My 45 degrees cut it into fourths, and so this becomes pi over 4. My pi over 2 is the same thing as 2 pi over 4. 3 pi over 4 squeezes here in the middle. 4 pi over 4 is just pi. 4 over 4 is just 1. 5 pi over 4 squeezes in here. 6 pi over 4, 6/4 reduces to 2/3 again. 7 pi over 4 fits in here. And then 8 pi over 4, or I just get back to 2 pi to finish things up. So again, that's an awful lot of information, but trying to explain it in terms of the pattern and how it breaks down if I'm looking at just the top half of the circle into sixths or quarters or thirds, and then working my way around and reducing my fractions because I love my fractions. The last part to add to this are the coordinates. So again, if the radius is 1, then when I start here, I'm going right 1 and I haven't gone up or down at all. So that's just at 0. If I go straight up, my x coordinate is 0. My y coordinate is 1. If I go left, I'm introducing negatives. Same if I go down, I introduce my negatives. All of these coordinates otherwise depend on those special right triangles that are up above. And so if you look at my 30 degrees, this 30 that I have here, if I drop straight down to the axis, if we think of it that way, that's a 30, 60, 90 triangle. So this is my 30 degrees. This height would be my short side, which was the 1/2. And then my 60 degrees here would be across from this square root of 3 over 2 is my base. So this point here has an x coordinate of the square root of 3 over 2, comma 1/2. What happens is that triangle gets reflected 4 different ways. If I flip left, this is the same exact point. I'm going as far left, it's just left, so it's negative square roots of 3 over 2 and 1/2. If I flip that down, they're both negative. So negative square roots of 3 over 2 and negative 1/2. If I flip it to the right, over here, then I have my positive square roots of 3 over 2 again because I went to the right. But I now have a negative 1/2. That then changes for my taller triangle that still has the same numbers, but they switch places. So now if I don't go as far over, but I'm going up taller because that is my 60 degrees, then the 1/2 comes first. 1/2 and then the square root of 3 over 2. It also reflects, and it's the same pattern. My x is negative and my y is positive. And then when I go down below, they are both negatives. And when I go over here to the right, I'm back to a positive and a negative y coordinate. So these values are so important because the x coordinate is the cosine of the angle, and the coordinate is simply the sine of the angle. Because if my hypotenuse is 1, opposite over 1, adjacent over 1. So it's just my cosine again, adjacent over hypotenuse, and sine is opposite over hypotenuse. So the only ones left to fill in are my 45, 45, 90s, which simplify to be the same because they're isosceles right triangles. And so for these, you just have to pay attention to the signs. We don't have to worry about the values. They're always the square root of 2 over 2. And then negative x coordinate, positive y coordinate. Down here in quadrant 3, I have negatives for both. And then over here in quadrant 4, I have a positive x and a negative y. So it looks like an obscene amount of numbers, but it's not. There are patterns with this. It's always 1/2 and the square root of 3 over 2. It's always the square root of 2 over 2. And I know that people have recognized this by looking at the values. If you go to the outside of the coordinate, so if I start here at 1/2, if you look just at the numerators, because it's always divided by 2, it goes 1, 2, 3. And then when I move over to my next side, it's still going 1, 2, 3 on my outside. And then 3, 2, 1. And then 3, 2, 1. If I go on the insides, it's 3, 2, 1, 3, 2, 1. And then 1, 2, 3, 1, 2, 3. The patterns are there. It just takes some practice and some remembering of how to graph these coordinate points, recognizing when things are positive, when things are negative, and simplifying fractions. It pays off, though, to have a nice copy of this in front of us while we're working with these trig functions.